good to be back here with some of the Orion CV folks. And we talked very specifically about how they applied LDRA in their project, and it was great to see the mission succeed. And this time I'm talking more generally about functional safety and how it fits in with upcoming NASA requirements. Very specifically, I'm talking about 7150.2D. I'll start a little bit about applicability, go into the standards definition of safety critical software, and then I'll dive into some of the details of the standard and talk about how it fits in with DO-178C, DO-326, and how to implement it. But before I do that, I had a little bit of a fun slide here. A couple little bits about flight software. In the early 2000s, myself and Chris Sloan were some of the early software developers at SpaceX. So we coded the Falcon base classes, and we used Rocky and Bullwinkle memes for all of the software. The only thing is, the Bullwinkle was in the software. Rocky was the rocket. We never wrote that down. So 5 generations of engineers later, people always come and ask me, what is Bullwinkle? Why is there Bullwinkle all over the software? On the left is myself and Steve Davis doing some late night verification of the Falcon vehicle software and the hardware in the loop. And on the right is myself and Hans Kunningsman, who often comes to these conferences, but because the organizers did such a great job of filling it, he wasn't able to get a ticket on our way back. When I left SpaceX, one of the things that I asked myself is, how do I avoid verifying software in the middle of the night? And that's what functional safety is. Functional safety, this is just an acronym, but functional safety is a set of procedures to make sure your software works the way it is supposed to work and make sure that you have the assurance that you can sleep at night knowing that it's going to work the way it's supposed to work. So it's been around for a long time, especially in the aviation space. And in the automotive space, it's become increasingly popular in the last few years, especially as digital logic has replaced analog controllers everywhere in the automobile. And it's good to see on the space side that we're getting more specific definitions from NASA. And that's what we're talking about here. So this is a specific standard for functional safety with respect to space vehicles. And it's relatively new. It's got an effective date and an expiration date, so we expect it to evolve and change in the years to come. And it applies to a lot of different projects, and I'll get into that shortly. It's a complete software lifecycle standard. It starts from the planning phase all the way around to deployment, management, on orbit, assurance, and going back to planning your next stage of your vehicle lifecycle. It has classes. The classes are ABC, just like DO-178, if you're familiar with that. DO-178, a Class A system, if you have a failure, the failure is catastrophic. In the NASA standard, a Class A system is whatever applies for human-rated space flight software. Class B and C systems relate to non-human rated ground support software and as well as engineering and simulation software. So the idea is you should have some kinds of verification and validation practices in all of your software, but there are certain things that are more highly recommended for human space systems. And before we get into all of the details, one part of the standard that I thought was really interesting was tailoring. Now, what is tailoring? Tailoring is how do we avoid doing the parts that are really hard for us. So the standard actually has a really good view on tailoring that allows you to ask for relief at any classification level and gives you a bunch of clear guidance in terms of how do you request relief? What are the appropriate reasons for, what are the appropriate rationales? Now, those may be risk, those may be budget, or whatever else falls into it. The other thing is, for every requirement in the standard, there is an applicability level for each of those A, B, C, D, and E levels. This standard is relatively new. It is specifically related to NASA centers, but we do expect it to be used in terms of commercial space. We expect it to be used in terms of contractors that are doing work in human spaceflight, because obviously we're in a world where human spaceflight is becoming more common. So the standard may or may not be your ultimate guidance, but it's a good place to start. Just like many times in the aviation world, people choose not to implement all of DO 178B. You can use it as a reference point, a starting point, and then fit into your business, your risk management, and how you fit in with the NASA contracting world. As with everything else, risk analysis, software hazard analysis is key to the standard. One of the key things that is defined is what is a safety critical system. So, it's especially applicable to safety critical systems. Safety critical systems are those systems that when they fail, your vehicle is lost. And safety critical software is the software where we're going to be tracking those hazardous conditions and how to deal with those hazardous conditions. How do we mitigate this? Well, the number one way to mitigate hazards is testing. That includes code coverage testing. You'll see at the very top here, I try to highlight the section of the standard. You can find the standard online and you can dive into the specific details. But I wanted to highlight some of the specific points that might be especially applicable to people who are writing software. One is code coverage, statement, branch, MCDC. So, statement is making sure all your lines are covered. Branch is making sure your ifs and elses have one test case on each side of the if and else. And MCDC is looking at your subconditions and making sure you have tests for each of those subconditions. Automation and working in the embedded platform are key to doing this right. Cyclomatic complexity is also called out very specifically. Again, I've got the little note to which part of the standard draws this out. And again, you see how it's related to different parts of the standard, A, B, C, and D. You should manage your cyclomatic complexity. Verification and validation. This, I thought, was one of the really interesting pieces of guidance, which I think went far beyond what we've seen in other standards. There's a specific guidance that if you're using auto-generated code, you shouldn't expect your auto-generator to do everything correctly. You should apply the same practices to your auto-generated code as to your hand code, because ultimately, whether the auto-generator generates it or you generate it, you're responsible for making sure it works correctly. Cybersecurity. DO 178 was done far before systems were connected everywhere. So in recent years, they came up with this DO 326, which is a bolt-on to add some cybersecurity constraints. But since this is a new standard, they chose to bring cybersecurity to the forefront from the beginning. So they have a whole section on cybersecurity, including cybersecurity assessments, cybersecurity tests, cybersecurity coding practices, and use of static analysis tools. I mean, I thought it was really interesting that we're able to do uplinks and downlinks from satellites with Iridium modems. I mean, that's great, but obviously there are a variety of cybersecurity constraints that need to be engineered from the beginning in our systems. Cybersecurity, there's no one piece that solves the cybersecurity puzzle, but a lot of it is around testing, making sure you have the appropriate requirements around cybersecurity, and making sure you're applying applicable standards such as CERT and CWE. Those are some of the key standards in the cybersecurity space. Again, these are checks to make sure your code works as securely as expected. Traceability. This is something also borrowed from DO 178, but brought to a bit of a forefront. Traceability is making sure your requirements connect directly to your source code and to your tests. So how do you do that? You have to make sure you have low enough level requirements that you can directly write them into specific tests. And again, you've got different kinds of guidance based on whether it's a human rated system or whether it's some other kind of system. Software requirements and traceability, we do have a variety of tools from that do that very specific piece of bringing in your requirements, normalizing them, connecting them to source code, and making sure you verified them. Software architecture. Software architecture is another key part of the standard, making sure you've designed your architecture and have appropriate design documents. And we actually go a little bit further, and we have a tool that allows you to verify your software architecture to see if your software architecture was implemented as it was designed. Similarly, for the lower level design, the standard asks you to look at your function level design and make sure your functions have an appropriate level of design rigor. Again, we have some tools to verify that your functions were designed as you expected them to be designed. On the implementation side, static analysis is called out very specifically, and this includes both standards-based analysis, complexity analysis, and security analysis. Again, following the V diagram, but I also think I'm going to just highlight again that number at the top. That's where you find this piece in the actual standard, the 4.5. Unit testing, making sure you have ways to make your tests repeatable. And this is another interesting one that was called out in this standard that I haven't seen in other standards, which is simulation. In space systems, simulation is key because our hardware might be really expensive or may not be available when we need to test it. So having some way to simulate it is great to incorporate into the process. Regression testing, making sure you can get the test to do the same thing again and again, is also important. In terms of tooling, you need to have some way to validate your tools. So this is in the DO 178 world, this is called tool qualification. You should have tests to make sure your tools do what they are supposed to do. And that's called out in section 4.5 as well. So to draw these bits together, some of the key elements: traceability, coding standards compliance, complexity, structural coverage, testing on a target or simulator, and tool qualification. These are all elements called out in the standard that are things that we've been doing a lot for a long time on the aviation side and the automotive side, and it's great to see them laid out in this much detail on the spacecraft side. So as I mentioned before, this is all very similar to what happens in DO 178C. Some of the differences are, instead of objectives, everything's in one big matrix in the NASA standard. So you don't have the objective tables. You have to dive into the big table and draw out the parts that you need. Safety levels are designed a little differently, and security is brought in from the beginning. It's not a bolt-on because it's a relatively new standard. In terms of implementation detail, we do have overall reporting that draw all these pieces together and allow you to present overall pass-fail. Do I meet the approach of the standard? And these are things that you can implement in a continuous integration system. So you can implement all of those elements from requirement traceability all the way down to your lower level tests running in your target simulator, getting your results back and drawing it all together. You can do it all continuously as part of your DevSecOps pipeline. And one of the things that we're working on that I just wanted to highlight is that we do have overall traceability reports that can show basically those big tables in the standard and show what parts that you pass and what parts that you can show specific evidence for. So we do have reports that draw in very specifically to those PR 7150.2D specifics. So that's all I had. I guess any questions?